back to like 2 weeks ago, 3 weeks ago. Melissa, you just watched this video yesterday, or 2 days ago, right? This video. Can I talk to you later about that? Okay, thanks. All right, Ian, come back to me. 3, 2, 1. Minute table. Give me a description, a symbol, something for either enthalpy or entropy.
Enthalpy is the delta H.
Good. Okay, so enthalpy is delta H, and delta H can be either positive or negative. Okay, everybody, what's the negative version of delta H mean? Energy is released. We can't lose energy, right? Law of conservation of energy. So it's released. So is that going to feel hot or cold to you if you're the hand? It's going to feel hot. And if energy or if enthalpy is positive, endothermic. Therefore, what does it feel like to you on the hand? Feels cold or lack of kinetic energy. Okay. Delta S represents entropy, obviously, because that's the only other one on the board. What is that measuring? Disorder, simply disorder. And so we reference states of matter a lot when we're talking about disorder. Again, you can have positive and negative on this one. So which one would be decreasing disorder? Positive delta S or negative delta S? All right, I got 3 people with me. I feel like this is like punishment. Let's call on you. You ready? Okay. So delta S, if it's measurement of disorder, what does a negative delta S mean, Alyssa? Less disorder. We got more order. Hey, less disordered, right? So what does a positive delta S mean, JD? More disorder. So that's kind of reviewing those big concepts. But this idea is going to apply to solutions. Well, what are solutions comprised of? Avi, what are solutions comprised of? Okay, so that you're thinking of like the state of matter, like a liquid and a solid can come together to make a solution. There are 2 really key terms that we usually use. Talk in your groups for a second. Let's get everyone on the same page. Terms we use to talk about when we put 2 things together to make a solution. You'll know it the minute you hear it, but. Michaela, tell me one component of a solution. So it's going to be aqueous upon mixing, you're right. Anybody else at your table? Oh, you guys are thinking like, think like 7th grade, like think way back. Mason. No. Solute and solvent. Who knew this? Solvent is a common term we use a lot for the liquid part of the solution, right? Like water, a lot of times is our solvent. And the solute is usually the what? The thing being is all like the salt or the solid or the powder. You're making Kool-Aid. I mean, whatever it is, this is the solution. These are the 2 primary components that are pulled together to make the solution. So we're combining thermodynamics and solutions, because solutions is our next unit. Who's already started looking at reading guide 15? You'll notice solutions, right? It's a lot of stuff about water and solvents. All right, so before I move on, you're going to work in your table groups for the moment. You're going to answer questions 1, 2, 3, 4, 5, 6 with a yes or a no on if you think that process is spontaneous. If you don't know what spontaneous means, read the background here for a minute. Just write down 1 through 6, and you'll put a Y or an N next to it. On the lab sheet. Yep, this is the pre-lab. This is the pre-lab reading and pre-lab questions. Talk it out. There's the definition of spontaneous if you need it, right there. Huh? All right, take like 10 more seconds if you need it. All right, Lindsay, counter table. What do you guys think? Ice melts when dropped in a cup of warm water. Yes or no? Spontaneous. Will ice melt when it goes in hot water? Will it? The answer is yes. So, quick review. What does spontaneous mean? It will just happen. You're not going to be like, all right, ice, I believe in you. Get it? You're not going to give the motivational speech to melt. It's just going to melt. It's just going to happen. That's a thermodynamically favorable process. Does spontaneous mean fast? Not necessarily. There are some things that will happen freely over time, but it could be a million years. Think of carbon. In high pressure conditions and high temperature conditions, what eventually happens to carbon? It forms diamonds. It's not happening overnight, right? That would be really cool, but it's not. But it is a spontaneous process. So keep that in mind. Next group, water evaporates when it's spilled on a hot surface. Jacob's table? Definitely, right? We know water will evaporate upon introduction to heat. Water in a glass on your deck decomposes into oxygen and hydrogen. Sorry, that's table. Simon's table? Maybe eventually over a lot of time. That usually takes some energy to make it happen, because the water, like in our water bottles or in a cup, it's not going to necessarily break and decompose. What's the water in the cup going to eventually do? Probably evaporate, but evaporation of water is still water. It's not a new compound. It's not individual elements. So that would require us to intervene. We'd actually have to electrocute it, and then it would do that. So not spontaneous on the surface. Okay. Ashley table, iron rust. Yeah, we've seen it happen. That's something that we know. We don't have to intervene. It's going to happen no matter what. Smell of perfume spreads around the room. Anthony's table? Absolutely, right? We're not going to try to scooch around the room. It's going to naturally happen. And then equal volumes of olive oil and vinegar dissolved together to make salad dressing. CJ's table?
No.
Why not? Right, there's no favorability for those two things to mix. So the olive oil is a non-polar thing. It's very oily, it's very fatty, and the vinegar is more like water. So we know water and oil don't mix together, and so you're never going to make it mix unless you put soap in it, which is an intervention. Okay, so I'm going to send you guys back to the lab. This is the first step you'll look at after reading the introduction to the lab. I'm going to give you some ammonium nitrate. I'm just going to kind of eyeball about 5 grams. You don't need scales at all. And the idea is that you're doing a little bit of review, a little bit of intro to new content, okay? So, same groups as yesterday, goggles, you bring the paper with you. We are only going to be back here for like half an hour, so let's roll. If you are reading the first page, and let's do this. Let's talk about reading. Somebody start reading, and I'll tell you when to talk for it. Read out loud your go. Read out loud your Popcorn if you're not done, and then you can begin as long as you're ready. You need to draw the first part. And all this is similar to what
So, you can fill in the blanks. So we gotta get you. Circle is the system.
Yeah, you're drawing that, and then you're following instructions, and I'm giving you. It's okay if your beaker is over 150. You don't actually have. Read every piece of instructions so you're following the right steps.
So weird.
really snippet and then like spat out. Oh yes.
Alright, so you're doing just a couple of questions and then you're proceeding. Alright, goggles up. I'll see you up here in 10, 9, 8. Bring your lap sheet with you. 7, 6. I'm starting without you. 5, 4, 3, 2, 1. Okay, so Malcolm's table. What kind of compound is it? Ionic, covalent, or metallic? Good, it's ionic. Make sure that everybody has ionic. What's the formula for ammonium nitrate? Brenner's table? NH4NO3. We took NH4 plus and we bonded it to NO3 minus. What are these two things called, Alyssa's table? Like this and this. This is the word I had your group work with me on. Marlena, do you remember? Just polyatomic ions, right? So we know that they're polyatomic, and I understand that ammonium, which is NH4 plus like this, I know it is covalently bound inside of itself, just like nitrate inside of itself is covalently bound because it's the only way to get two nonmetals together. But this bond between the two ions is ionic. So that's why the best answer there is ionic. I know you were thinking, oh, all nonmetals. That's totally covalent. Okay, ammonium nitrate is an ionic solid, okay, composed of what? What builds up that solid? Say again? Just ions. It's just a bunch of ions together. So you guys were like, I don't know, what word could this be? What word could this be? Ions. Okay, so you saw in the reading it talked about the orientation. Make sure your image or your diagram is indicating this. If we have, and I know I have sodium chloride here, but it's the same premise. What is a positive ion called? Cat ion, because cat ions are positive. Remember the cat? Positive. All right, so the cation being positive is going to be attracted to which part of water? The negative aspect of water, which is the partial negative that's held on the oxygen region. But then this negative guy is called a what? Anion, and it's attracted to what part of water? The positive. Opposites attract, which is the Mickey Mouse ears, the hydrogen part of water. So they had an exam question like this, I don't know, a couple years ago, and they don't give you the diagrams at all, they just talk it through. They're like, which part of this would be attracted to which part of this? Well, it's super easy to think about if you have a visual, which is, this is the visual you should be thinking of or drawing for yourself. Okay, so the physical state, okay, so number 4, what basically happened as the ammonium nitrate dissolved? Did entropy go up or down? Loud and proud. Increase. Yeah, it went up because you went from a solid form to an aqueous form. Aqueous is getting crazy, right? So this delta F should be positive or negative. Definitely increase in meaning positive. That's this one. That's increase. That's positive. Okay, so how about the water molecules? You guys read that the water molecules could freely move about, but the minute we put ionic solids in there, the water is basically attracted, and they were like magnets to the ions. Were they freely moving at that point? As much? I mean, they're still free to move, but they can't move as much because they're stuck kind of attracted to an ion. So what would this be? Positive or negative for the water? That's a negative for water. Overall, did the process of dissolution of ammonium nitrate occur spontaneously? CJ, why are you saying no? Did you have to stir it?
Well, eventually I might, but
If we, well, for it to occur in a reasonable amount of time, which is time is not, spontaneity is not contingent upon time. For us to see it occur, yeah, we stirred it, but we didn't have to. Would it have dissolved? Totally would have. Just like sugar would dissolve and salt would dissolve in water over time. Just looking at it forever, you're not going to see it, but you know, it definitely will. So I would say yes, it is spontaneously occurring. So overall, if it is spontaneously occurring, which was more favorable? The delta S for the ions or the delta S for water? Good, the ions were the ones that drove the whole process. The ions were a positive delta S, whereas the water was a negative delta S. This must have been a much bigger value to drive the overall process to occur. All right, so that's our entropy talk. Enthalpy, everybody got a reading. What was our delta T? Was it going up or going down? Okay, so here's your calcium chloride in water. That chemical reaction, or that chemical dissolution process was the system or surroundings? This is our system. Okay, so the system was held in a surrounding. It was held in a beaker, and what did we put in the beaker? We put a thermometer with, of course, the water was already there. So here's our beaker. We put a thermometer in here. Okay. What did we observe on the thermometer? Temperature increase. Okay, so the delta T was positive. It was increasing temperature. So who was providing that energy to the thermometer? The system was, right? So the system was giving energy off to the thermometer, which was the surroundings. So overall, would you consider this change endo or exo? Everybody, come on. It's definitely exothermic. So that process, if it gave off like 20 degrees Celsius, your hand around the beaker would have felt that. But I wanted you guys to let the thermometer do the job so you understood the thermometer is just a fancy hand. All it is, it literally has a reading on it though, whereas your hand's like, it's getting pretty hot, but you wouldn't know how hot it got. So it's the same scenario, but we use a thermometer instead. So is this delta H positive or negative?
Positive.
Which one?
Negative.
Negative means exothermic, remember that. That delta H is negative. So the energy was lost or released from the system. All right, open back up my website when you get a chance. We're going to add to this, and if we don't finish it today, we'll finish it tomorrow. Go to Unit 6, Part 2 docs. Let me just verify that. All right, so let's get rid of that. Go to Unit Docs. When you go to Unit Docs, Unit 6, Part 2, Thermochemistry, and click More, there's some solution stuff on this page. And if you look down to see Molarity Worksheet, WS, Molarity Worksheet, after you hit More, we're going to, we'll do this for about 10 minutes. We'll see how far we get, and what we don't finish, we'll finish tomorrow for warm-up. Okay? So when you click on the Molarity Worksheet, it looks like this. You can work in your table groups, talk it out, write this on the same paper you're writing your lab sheet on, or you can kind of get all the solutions up together. It's pretty easy stuff, like solutions wise, before we have solutions. So talk it out with your members at your table.
Water literally says it is.
reading